Thank you very much. As you say, welcome to the last talk of the day. Well done. You've all got through a lot of talks, I'm sure. Yeah, I do have to temper some expectations at the very start of this. It was only ever a model of a chemical plant, just in case you ever read that and thought, wow, I got to play with an actual plant. I'm afraid I didn't. They wouldn't let me. I did ask, but such is life. Okay, so who am I? So for the purposes of this work anyway, I'm a doctoral researcher at Brunel University. That's a fancy way of saying postgraduate students. That's kind of part-time now because my full-time job is a security analyst at Threat Spike Labs. We have some of my colleagues at the front. We do red teaming, SOC, pen testing, all that jazz. It's very fun. Come talk to us. And in my prior life, rather than being doing computer science stuff, I actually used to be a metallurgist at a chemical plant. So that's where this has kind of come from in a way. It's informed some of the studies. But I also liked computers, so that's why I made the move. Yeah, just FYI, if you think the job of a metallurgist is hard, for the most part it's not. You look at that and say, that's rust, that is. There you go, there's your degree. That said, one kind of link, there is actually quite a lot of materials fraud that goes on in these things. You might think everyone's kind of nice, but if you start looking for fake stuff in expensive equipment, I guarantee you'll find it. So if you're thinking of a career change the other way, something to bear in mind. Okay, first, some history, because this is my talk and I want to do it, and because I think it will be useful in informing our current approaches. So, really, this whole thing started with the Industrial Revolution. We worked out how to utilize coal and steel and steam to replace manual labor. That was a huge thing. I feel like we don't talk about it enough, but there you go. So we did that, and then swiftly after that, we went even further. We invented flammable liquids. We invented the processes of moving them around and using them. We started with Bakelite and other petrochemicals. We started with combustion engines. And yeah, as you can tell, that's completely revolutionized society. But it did come with a downside. And I'm not talking about carbon dioxide for the purposes of this talk. I'm talking about the general concept of risk. So with these things, you do get some fairly funky interactions. My specialty was acids rather than hydrocarbons. But you do get aromatics, which do God knows what. You have very interesting atmospheres that before all this stuff, we just had air or hot air. Now you have like 100-degree vapor phase equilibria of acetone and other weird things, and working out what that does is hard. And if you really want to scare yourself, become acquainted with the concept of a boiling liquid expanding vapor explosion, which is when all those atmospheres start to meet each other. This little picture, in fact, isn't BLEV. Anyone know what that was? Yes. How close were you at that time? Yeah. Yeah, it was quite fun. I mean, I was a few miles away, but it's still underneath the cloud. So yeah, previously, when all this stuff was done with manual labor, it couldn't go that wrong. When we introduced all these chemicals and all this hyperscaling, just like computers really, it has the potential to go wrong at a larger scale. The interesting thing, however, is for all the amazing number of ways you can die in a chemical plant, they're actually really safe. So the place I went to, the biggest hazard by a long way was 50-plus-year-olds spontaneously dying of heart attack. So I think that's something to be proud of. So, in relative terms, so how did we do this? Well, we start out with control theory. This has analog origins, with something like Maxwell's paper on governors. This is a fairly simple device. It's just a kind of centrifugal clutch type thing. If your device is spinning faster, the balls go out. That moves some springs and reduces the inputs. That's kind of our first automatic negative feedback thing. Possible fun entomology fact. That may be where the phrase balls out comes from. Take them out, you have no feedback, so the governor's just going full speed. That paper's actually criticism of this mechanism, but never mind. However, in the 20th century, that's where we really start to get into the meat of it, and it's where it starts to become relevant to our conference, because we start working out that these computer things can do useful stuff. So we started talking about Laplace transforms and complex numbers, something called the Nyquist stability criterion, which, anyone got an idea what that funky-looking Nyquist plot is? Oh, that's the pitch response of an F-16 fighter jet. So what we did is we just thought of it like another plant that has an input and output, and if you know how to read these diagrams, you can say whether your machine is stable or unstable. You can then do all the really complicated maths necessary to keep it stable on something like a PLC. Great. We discretize things. We have some advances in matrix-based control theory. We have this great paper in 1978 called Doyle's on Guaranteed Phase and Stability Margins. I don't much like the actual paper, but the abstract is great. It is, there are none. It's basically saying you can't prove safety in the concept of arbitrary noise, which I would have thought intuitive, but there you go, 1978 is when we proved it. So we got all this stuff, and then once we got these PLCs, we start integrating it into the higher order business processes. So these things will maintain a set point, but sometimes you might want to change that. You say, it's winter, we need a different fuel formulation, or a refinery somewhere else is overproducing or underproducing, so we need to coordinate that across multiple sites. That leads us to integration and the kind of Platonic ideal of, you may have heard this in the talk earlier, the Purdue reference architecture. So it kind of looks like the OSI model in a way, almost, maybe. So you start out at the very bottom with actual physical devices, sensors and actuators, things that move. They might not even have computers in. Then just above that, you have fairly low-level things, PLCs, safety instrumented systems, which are always fun, base stations, things that probably are running real-time OSs and doing a fairly limited subset of things in bytecode, and they're just following higher-level orders. You then have human-machine interfaces and engineering workstations that help to present this to users. If you're interested, that's not a mistake. There does seem to be some disagreement as to where engineering workstations should go. These engineering workstations, HMIs, they're where you might start to see the transition to, just like Windows boxes, and things that you might consider within the normal realm of IT. But because they're in a plant, they'll be at least 15 years out of date. I feel like that can just be taken as read now. Anytime people say OT or control systems, they go, so it's 20 years old. And then as you go up, you go through a DMZ and then into your business processes and the kind of wider cloud and squiggly stuff. Okay, so what do we also do as current defenses for safety at the high level? So you may have heard these terms again before if you were in the train talk. This is UK-specific regulation. Obviously, different jurisdictions have different names for it, but they tend to be kind of the same thing. They're basically saying report to the government, have a process to enumerate your risks, much like cyber risks, really. We do something called a HAZAN, which is just very methodical for each part. What happens if it does too much of what it's supposed to do, not enough, stops entirely, and honestly a couple of other things that I forget. But it's going through every single component. And then we do something called a safety case, which is a really long document. 10,000 pages and £10 million would not be unheard of for these things. And all that is a piece of paper that's arguing why you're safe to operate. So these are kind of legal instruments. One thing I do want to bring up is, for all that, you can, in safety, talk about something called the Swiss cheese model, which is basically saying we have a layer of defense here, and we accept that it's not perfect, but beneath that we have a second layer, and for accidents, you kind of need these metaphorical holes to line up. I know it's a bit abstract, but yeah, what we're saying is that all of these different layers of defenses, static defenses rather than intrusion and response type stuff, can still be useful. That to me is the interesting point, because that's different to security, where if you just have lots of static defenses, that might slow your attacker down, but they will learn how to get through all of them. Yeah, cool. So, after that, I'm just going to go through a couple of historical attacks and incidents. Sometimes one that was claimed to be the former turns out to be the latter. That is actually quite common. These will be necessarily brief. It pains me to have cut a couple of them, but such is life. Okay, so probably one of the most famous in ICS circles that we hear about is Maroochydore. That was just a sewage plant in Australia. And it's a very classic case of a contractor who was fired. They didn't revoke any of his keys or tokens. I say tokens, I think this was pretty certain this was Telnet. So it's 1999. So yeah, he logged in, started kicking out legitimate operators, opening valves willy-nilly and just wrecking the place. In total, there was about 250,000 gallons of sewage released directly into the environment. The fine then was 600,000 Australian dollars, so it's probably about double that in total external costs to society, and you'll have to adjust that for 2023 dollars, so probably about triple this. Okay, the most famous, of course, no talk can be complete without it, is Stuxnet. So this was definitely advanced persistent threat actor. Famously got through an air gap via using infected USBs. They also, if you've looked at the source code, they implement a lot of safety checks to make sure they were only targeting Iranian plants, particularly the Natanz plant. So once it got in, the end effect, the thing I was interested in, was how it did damage, and this is a lovely bit of physics. What you do is you cycle these things up and below, so repeatedly past their resonance frequency. At the same time, you report to the control room that everything's okay. This does seem to be quite an interesting communications difficulty with other chemical engineers. They don't seem to get the idea that if someone has arbitrary code on your PLC, you can't ask the PLC and expect it to be truthful. It'll just say things are okay. But yeah, that's a practical tip for you if you're actually talking to chemical engineers. That does seem to be one of the difficulty points. But yeah, whilst this does sound very scary and dramatic, and in a way it was, one of the key lessons from this, I think, is that human operators were present in the actual rooms where these were, and they noticed the side channel of the frequent changes in noise. So they said, I don't care if your thing says it's fine, it's clearly not. And the end result was, whilst this slowed the enrichment process, it didn't actually stop it. So it's actually arguably, it's pretty debatable whether the actors achieved their goals in this one. Let's move on to the oil sector. We had a big refinery in Saudi Arabia infected by Triton malware in 2019. This was quite scary for me personally because the safety instrumented systems were directly hit, and they're something that, in comparison to regular PLCs, really doesn't need to talk to the outside world all that much. Yeah, the interesting thing about that was, whilst that happened, whoever did it didn't bother to put in a payload. We still don't know really. Of course, I'm only going off the same public information you have. But yeah, they went to all that effort. I mean, you can take some guesses as to who it was, and then nothing happens. Another great one that made the news, of course, in the oil sector was the Colonial Pipeline. That was actually only the IT being hit, but, and here's a very common thing here, The OT operators will be very sensible, and they will say, if we can't guarantee that our stuff is unaffected, then of course we'll shut it off. That sounds good, but alarm fatigue is a thing, and that did mean that this had a real, 8-figure, roughly, cost that could have been avoided. It's still the right call, but yeah. Okay, so moving on to steel. Some people have decided this isn't a chemical plant. I disagree. There's some interesting and conflicting reports. There was one that was supposedly a German steel mill hit in 2014. This source came directly from the German government or a sub-department of, and if I'm honest, I think this may have been a translation error, because there's no other records of it, there are no private records, and there's no obvious dip in output from Germany at the time, which you would have expected. The report is great, it reads like a great description of how you would attack the plant, but I'm not sure I think that's what it actually was. However, various steel plants in Iran have been hit. This is a still from something released last year by Group Predatory Sparrow. They quite nicely waited for people to leave the room, and then they dumped the entire contents of this steel billet on the floor. So that will be fun for the operators. I mean, I honestly couldn't put a dollar figure on how long that's out of action for and the cost, but it's going to be a lot. Okay, finally, water. So again, this is another concept of an attack that probably wasn't an attack. This was Oldsmar. There was an apparently open team viewer session that was just accessed by an unknown actor, and the sodium hydroxide concentration set to a very high value. Honestly, from later reports, for a start, just because the set point was made very high doesn't necessarily mean the system can actually achieve that effect. The calculations I did, you'd probably only be doubling the concentration, and it would be nasty for the 50,000 or so people drinking this water, but not like the, oh my god, everyone's dead thing that was going around the news at the time. To pour further cold water on it, as it turns out, that was probably almost certainly a legitimate operator who was momentarily confused. We did have slightly more recently some hacktivists deface some PLCs in a pumping station in Pennsylvania. This was a smaller plant, only about 3,000 people affected. And once again, actually, it was a successful case of reverting to a manual backup. So there were people there checking the pump rates and so forth without using the PLC. It still worked. It was fine. So, yeah. So, what next in this field? So, we already have some systematic desktop exercises and talking to regulators. What I want to do is complement these with probabilistic methods. So what we can do is try a lot of different situations at the same time. And yeah, go beyond this Swiss cheese model, because like I said, if it's an attacker, it's not coincidence. They will deliberately find the worst ways through. Okay, so now on to the meter. It's some automated wargaming. So I'm afraid some maths has to happen. I've tried to keep it to a bare minimum, but it's some. So if you're a budding researcher these days and you want to do a computational method, what are you going to do? You're probably going to use machine learning, right? In particular, I'm going to use a subtype called reinforcement learning. Now, this one's interesting because it doesn't have a static data set to learn off. Instead, what we have is we have a mock environment. So in our case, that's the chemical plant. And it will send to our agent, which is the thing that's doing the learning and trying to control something, an observation. And it will also send you a reward, which is just a scalar number. Higher rewards, better. The agent, because we're academics, we like Greek letters, implements a policy that we call pi that just takes that observation, sometimes called state, it will vary, and says, given this state, what do I do? So it's just basically a giant if statement, and takes that into an action. The action sent to the environment computes a time step. What the agent wants to do is it wants to maximize the long-term reward. So you often get this criticism of, wouldn't an agent do the best thing, even the best thing was figuratively jumping off a cliff? The answer from a naive perspective is yes. That's why what the agent will do is learn multiple runs of long sequences of rewards, and it will apply a discount factor to say, what I really want to maximize is the reward I get now, plus the reward I think I'm going to get next, plus the reward after that, with some form of discount factor to say, weight the ones in the future less. You also have some form of noise term just to make the agent occasionally do random things. That's just to let it explore what it can do more. Okay, so here's my setup. We're going to go for an assumed breach of a particular test bed. The extent will depend on the scenario. I'm going to do multiple scenarios. It is, I'm afraid, going to be protocol agnostic. So initially, I did actually put in some Modbus emulators, but they don't really change the results because you just get the same conclusions of, well, the attacker can do anything. They can do anything regardless of whether they're using Modbus or Symantec or similar. So it's just a maintenance headache, so I took it out. So yeah, we're going to go through multiple scenarios with this test bed. That's the test bed. It's actually, believe it or not, a fairly simple plant. It is kind of made up. It's a very common one to use as an example of, can you control a plant in general? But the internal chemical details don't matter all that much. Mainly you want to look at these three main vessels, the reactor, the separator and the stripper. Again, what they do is actually not particularly relevant, but the levels and situation inside them will be key. It's got 12 manipulated variables, so that's the things that you can alter, and 41 things that you measure. So that's your kind of inputs and outputs. And what you're trying to do is produce a lot of G and a lot of H. Again, these are actually made up products, but they're, roughly speaking, an organic chemical of weight about 100. The other last thing I want to point out here is my version actually already has a traditional control system implemented with PLCs. Okay, so this being Wargaming, we can't just have one agent, we have two. So actually, conceptually, that's probably one of the easier parts. We just go, instead of the environment sending its thing to one agent, it sends two observations and takes two actions. And we start with our scenarios. So I'm defining those as, what can the blue team do? What can the red team do? And what does the red team want to do? So we are trying to mimic some different threat actors here and different levels of blue team competence. The cheeky bit is this capability also has a huge impact on how you would program these agents. I'll talk about that in a minute. So yeah, for the red team, the intent is going to change what its reward is. For the blue team, it's always going to have the same reward. It's going to try and keep the plant operational and running and producing. And yeah, the red team by default is just going to oppose that. So if I don't say, that's what it's trying to do, but it can have different sub-goals instead. Okay, so action spaces, aka capabilities. So there are two different ways to program these agents. There is a really simple way, which is saying I've just got a menu of things I can do for each time step. So in this case, I can reset a PLC and run it as a kind of manual backup for an hour. That would give the SOC time to, remediate a smaller infection, say. Or I could shut down the whole plant, incur a huge cost, but hopefully give your IT guys enough time to completely remove an infection. Or I could just do nothing, which is what you'd like to do. The red team, if they're a fairly low capable actor, they're going to be doing obvious things. They're not going to be subtle. So they're either going to change things to high values or low values. And I've given them the ability to alter any of the measured variables, any of the manipulated variables, or any of the set points. So this actor is not sophisticated, but they do have pretty much full access to the plans. For a more sophisticated one, this is where the blue and red team both have like fine-grained control, so they can continuously change a variable, make like small changes rather than massive ones. The blue team has full control of the plants. The red team does not, but it can spoof signals and it can change set points still. The reason for splitting it this way is, again, the discrete ones I've called here, aka kind of low capability, fairly basic ones, when you just have a menu of things to do, that's fairly easy to program because you just go, well, what's the value of each of these options? Great. Pick the one that has the highest value. Right? Easy. The continuous agents require something called deep deterministic policy gradients. It's a form of gradient descent, and I banged my head against the wall for hours trying to get a slide that could explain this well. It's very difficult, so we're just going to accept it for what it is for now. If you want to have a go at programming those, you're welcome to try. Okay, we're also going to do one last variant for the blue team, where the blue team will be assisted by its own process model. So hopefully what it can do is, instead of learning from the past, it can ask this twin, what is going to happen over the next 48 hours given the measurement that I've just seen, and hopefully react based on that. Okay, so finally the reward functions. So overall, the blue team will get some fake money for producing stuff, provided it produces a product that is good. So it has to be within a certain balance of chemicals. It will pay for utilities that it uses during that time. It will pay an environmental penalty if some of the purge that it dumps into the environment has, I've arbitrarily decided that G is going to be extra harmful. So you get a penalty for that. You also get a fixed cost for the CO2. So the blue team is trying to optimize for all these things, but for the most part, it's probably not going to outperform the traditional control system. I said the red team will just have the inverse of all these things, or of a subtype. So the red team is trying to say, don't produce anything, or produce it out of spec. That turned out to be quite common. Or shut the plant down. Or ideally, if it can, overpressurize the reactor, at which point you would get a huge reward for the amount of damage done. Okay, so this was the initial set of hyperparameters I used for training these networks. I think that's the latest set as well. It might be a couple of generations old. Unfortunately, this part does seem to be mostly trial and error still. What I will say, you can get good results even with a fairly small network, or at least what you'll find is networks will often coerce a lot of their parameters to zero, so just adding more layers does not necessarily help. Okay, so on to the results. So this is our low capability scenario. This is before training. So as you expect, at the start, they're just acting effectively randomly. So they have this noise term which will decay as training goes on. They're just exploring what happens here. They are baby fresh agents. They have no knowledge of the world. They're just acting randomly and seeing what happens. What happened in this one is that the production was out of spec, so the blue team has gotten essentially no reward here, apart from occasional spikes where I guess it must have drifted in spec. The control system was fooled, so the control system had its set point changed by the red team and went, oh, I'm supposed to make the stripper level really low, And so it does so. In this variant, it actually seems to commonly fail by draining the reactor in order to do that. But it still manages to fail within about 200 seconds, which is about 3 minutes, which is frankly not enough for a incident response team to do anything about it. A common feature we've seen actually is this blue trace, which is coolant. So that's basically gone to zero. So very frequently in these scenarios, the reactor coolant was also switched off. Okay, after training, the summary of it is the red team won. So at the start, we had it going down in about 200 seconds. Now the red team can take it down in about 20. That's definitely not recoverable. So it's actually using the same sort of actions. In particular, it was changing a set point for the reactor level and saying to the control system, you should drain the reactor. The control system then does that. That's easy enough. Again, it changed the coolant, so it decided the reactor shouldn't have any coolant either. Unfortunately for the blue team, all this agent learned to do is basically to do nothing. So it's actually at the very bottom here, and it's choosing an action that is very safe. So it won't cause the plants to fall over, but it won't effectively respond to a red team activity either. That said, the blue team does manage to produce some products for 20 seconds this one, so it gets a small win, I guess. One thing I found is that sometimes the red team would go haywire just even if there was a situation where I had no blue team involved at all, just the red team. So this was something after training. It was supposed to take the plant down, as we saw previously. But in fact, it's managed to miss that strategy and it's done random haywire over here, but it's not really been very effective at taking down this plant. That's a shame. I would say it has managed to burn a lot of carbon here, I think. So it has been rewarded for taking away a lot of the operator's money and producing no products. So that's kind of a good goal, if you're red team. Cool, system large trace. This is actually the same, not quite the same one, a very similar one. I just wanted to show what was happening to the control system. So again, this had a set of PLCs and mimics PLCs. And this error is saying how far away from my set point am I? So what we see is when the set point is changed, the error suddenly becomes massive. The control system freaks out and basically saturates. That's predictable for the discrete one, but was interesting when we get on to the continuous one. The other interesting thing from this one is we started seeing a oscillation in reactor pressure at around about 165 seconds, and that was constant across a lot of different scenarios. So that's not something I think anyone's ever seen in this testbed before. Okay, so we're moving on to the continuous models. So what I was trying to get these agents to do here is find ways to have a big effect on the plants by doing lots of little actions together. Particularly one thing I was trying to mimic was fatigue losses. So in a real plant, what you can do is just turn a valve up and down a bit continuously, and that will wear it out eventually. And that's great because a lot of the current defenses say things must stay within a certain range, right? They must stay within these safe states, but they can transition between them as much as you want. And that means, yeah, that's a potential avenue to evade current defenses that I thought might be interesting to see if the red team can learn this. One thing I found is that whilst the red team can do anything, can do every single action simultaneously, these agents really seem to collapse on doing just one thing. I'm not sure why that is exactly. It seems to be quite a common feature of neural networks, but there we go. So yeah, this was pre-training. It's still mostly noise, and the red team manages to break the plant in 80 seconds, which is quite fast. What it didn't really manage to do is learn how the plant works. So This dotted line over here, that's roughly speaking a loss. It's saying how accurately do I know what the plant is going to do next. Lower number is better, and as you can see, it's actually rising, so it's becoming worse at predicting the future. After training, it does settle down, but it's still at like 10 to the 9, which is quite a high number. It's arbitrary units, but it's still high. So that's showing there's still quite a lot of confusion in this agent. So if you're good at programming neural networks, talk to me. If you can get a better one, great. So this one learnt just to do one thing. It still have managed to completely overwhelm all of the control system just with this one error, just with this one change. So that's the purge gas fraction, which should be a fairly minor thing that the chemical equivalent of a blue team wouldn't necessarily look at. But yeah, they managed to kill the plant with it. Again, we start seeing an oscillation at 165 seconds. Never seen this before in this plant, but it's quite cool. And then finally, the version I had that involved a twin. This is pre-training, so it won't be very good yet. The blue team won't be. Again, we see the same oscillation, which seems to be linked to the loss of coolant. So it's saying even if there's nothing going into the reactor, if you lose coolant, I guess you'll start this oscillation. Yep, and one thing we found is that whilst the total loss, so the inaccuracy of this agent, blue team agents, was slightly lower than the fully continuous one. It was still quite high, but it also often tended to immediately spike just before failure. So that's quite a good indicator in the future that if your twin is no longer accurately predicting what's happening, that's good with saying things are going badly, right? Normally, your twin should be making accurate predictions. Okay, so my conclusions from this. Most of the red-blue engagements, with the exception of the low-capability ones actually, converged on a shutdown in about 165 seconds. So 3 minutes, that's not really good enough for a blue team. They need a bit more time. I did get a few that extended that to about 10 minutes. That might be enough to do some things, but probably not enough for a full IT response. Discrete engagements could be even faster. The other things I learned, the red team didn't pay attention to its reward function all that much, and the blue team mainly learned to do nothing. So these agents could probably be a bit better. Yeah, like I said, if you're interested in programming neural networks, talk to me. And finally, visualizing 51 parameter control schemes is a real challenge. We did have a live updating version of this one, but unfortunately papers need static things, and even managing that as a dashboard, there's still a lot of information, which is probably why we normally subtype it and have teams doing this sort of thing. Okay, so for future work, I'm looking at particle filters, which is a fancy way of saying do all of those twins in parallel. So the way that works is instead of doing one, you ran a bunch of twins at the same time, and then you do some probability logic, some Bayesian stuff to go, what's the most likely explanation? What's the best fit? And then assume it's that and work based on that prediction. I'd like to integrate some better prediction engines into this. So, for example, all of these neural networks were stateless. Again, that's the thing that's, I think would be a great avenue for further research, because real chemical plants, of course, aren't. They change states slowly. And in particular, if you're trying to detect an anomaly, you can have a piece of logic saying alarm if you're outside of these ranges, but in reality, a plant that's oscillating wildly within those ranges is still alarming, and indeed probably you're having spoofed data. I'll be tempted to integrate more layers of the Purdue model, particularly alarms, because if you go to a real plant, if an alarm is blaring, you don't go in, that has a real impact on operations. And also, that leads to alarm fatigue, which I'm sure at least some of us are aware of. maybe integrate some of the more human reactions. So currently this was just like defaulting to an open loop control, which is fairly primitive. Humans could help that a bit better. So I'll be interested in integrating that. And finally, some more complex plants, like particularly the vinyl acetate model, which has been used as a testbed for security before. Okay, that's all. Thank you. Thank you. And are there any questions?
Thank you. Thanks for the talk. I just have a question about, do you think that any of these models could potentially accurately predict any targets that any threat actors might have within a real-life plant? And do you think that it could be maybe incorporated with a lot more variables, like you said earlier, that is the intention?
Sorry, could you repeat the first part of the question?
Oh, yeah. Do you think that the models that you created could accurately represent a threat actor targeting a plant? And do you think that it could potentially reveal potential aims and targets that threat actor might have for the plant in particular?
I hope so. So my main goal for this was to make the test bed, right? So it's based on OpenAI Gym actually, and it's just adapted to do blue team, red team stuff. I think OpenAI Gym themselves have done some odd things in that space, so I'd have to recode it, but such is life. Potentially, yes, with a good enough neural network. Again, that's why I put these in as I hope they're good proof of concepts, but you can basically spend forever tuning neural networks. It does still seem to be a bit of a black art, so I think ultimately, yes, they could, but as with a lot of machine learning type questions, whether that happens in 2 years or 20, I couldn't tell you that for sure. Yeah. Yeah, there's a microphone coming up.
Thank you. And I do have a question, because you're using reinforcement learning. If you could, for example, in your method, is it possible to apply multiple agents on both sides? For example, blue team, three blue teams competing for the reward to prevent the passivity of the blue team, and for red team also potentially to prevent the fact that reinforcement learning sometimes just picks one thing and just keeps repeating it to get the same reward, because it knows that the same reward is going to keep going.
It definitely falls into the trap of, repeating the one thing that gets a reward, yes. Interesting idea. I'd say I wouldn't do that for the blue team. What I would be very tempted to do is have multiple state prediction engines in it. So I'd have the same state to action mapper, but with lots of things saying, what do I think the state of the plant is going to be? What do I think the reward is going to be? And then you could do something, either picking you could do something with some Bayesian maths in it. I'm not sure what, to pick the most likely of those. So that's basically what the particle filter would be. Multiple red teams is even more interesting. I suspect that would just be even more chaos.
Thanks. So these systems that you're setting up are pretty much at the level where an attacker is already in the system and is able to take these actions. So to sort of use that metaphor for an IT situation, this is when the attacker already has domain admin and is about to execute the ransomware.
Pretty much, yeah.
At that stage, there are ransomware mitigation techniques, but they're really a best effort situation. So is this model you're looking at to try and work out best effort actions, or is there something different in the sort of OT and below model that means it's better than best effort?
Yes, I'd say that's roughly correct, yeah. I would have said when I was going into this, I could probably tell you at least some of the results, which are, if you've got the equivalent of domain admin, as we saw, the red team has a very decided advantage. We have some very, very, very rare runs where the blue team can respond and take the plant to a whole hour. So we effectively decided if the blue team can run it for an hour, that's considered a win. That's not a long time in chemical plant stuff, really. I did also have one implementation where the red team had control of just one PLC. But yes, we abandoned that after a while. I'm not really sure why in retrospect. But that might be an even good testbed for assumed partial breach.
Hey, thanks. It was a really interesting talk and really incredible what you put together. So the neural networks that you used were quite shallow and quite small. And there are a lot of optimized for reinforcement learning networks out there. And I was just wondering if because the networks were quite simple, that what you end up is that chaos ends up winning, because the networks are all so simple that it's harder, it's more complex to fix the problem than it is to just break it. And that sort of maybe by really working on maybe more optimization on that side or a different choice of model, you might get different results.
I'd certainly partially agree. So my reason for being cautious and having relatively shallow networks is they do tend to collapse quite quickly. I'm sure if you've seen this, you can have a network with billions and billions of parameters. And if you don't get the architecture right, you end up with almost all of them doing nothing, right? I don't know if you've seen that. That's quite common, so I wanted to avoid that. I put, the softmax layer in to try and convince it to do one action, because that was easier. What I did find is even without that layer in, it was still tending to do just the one action, even if it could do 15 different things. What was the second part of the question again? Oh, it's chaos wins, right? Yes, I'd certainly agree. So the real challenge for these networks is they need to understand what's going on before they can properly remediate. Also, if I'm going to be honest, this was done on a fairly low spec desktop. So there was limited bandwidth for training large networks. So it's going, if this took 3 times as long to train, but didn't produce noticeably different behavior, go back to the simpler one.
Okay, I think we need to end now. Thank you very much for your talk, Martyn, and a big round of applause. And if there are any further questions, I think Martyn would be happy to answer them in person.
Yeah.